So what you can see on top of the page, you can see if nx equal to ny. So nx equal to ny means they have the same sample, the number of samples, same for sample x and sample y. And if every piece of data in x is somehow linked to a piece of data in y, then it is paired sample. Okay, so they are linked. Data is linked. For example, x is IQ before and y is IQ after you use the crystal. So that is linked together. The data x and data y are linked together. So then we can use pair sample. So a new set of data is created. So we use d equal to x minus y. Okay, x minus y. So for example, one believes that his mystical crystal can boost IQs. He takes 10 students and records their IQs before and after they have been blessed by the crystals. The results are, so you can see the results here. Okay, so it seems like this one increase, this one same, this one decrease, and so on. So tests at the 5% significant level once claimed. Okay, so based on the information here, we need to create a new set of data by using d equal to x minus y. Okay, so I put d here as the new row. So what we can do is we just minus. We minus. So which minus which? It doesn't really matter one actually. So let's say I take d equal to IQ after minus IQ before. So then I will get 1, 0, -2, 11, 5, -1, 1, 3, -1, and 5. So we get this set of data, which is D. Okay, now we set up the null hypothesis. Null hypothesis, we assume there is no difference. Before you use the crystal and after you use the crystal. So if there is no difference, the mean for D should be 0. No difference. H1 mu D. Okay, so we follow this one. Can boost IQ. So if they can boost IQ, that means after using the crystal should be greater than before. So that means should be positive. So more than 0. So this one can boost IQ. This one is the hints to set up the H1. Okay, then we continue. We have to use D. Yes.
Instead of this, can we use like after minus before instead of difference? So after minus before is 0 for the initial hypothesis, and after minus before is more than 0 if proven.
You mean after minus before for?
Yeah, for these two.
For these two. Yeah, we are using that now. We are using after minus before. Yeah.
But we can write after minus before instead of difference, right?
Yes. You can use words instead of equation like this. It's fine actually. Yeah. Okay. So now let's continue. So we just need to find out the mean. The mean for the D. Okay, the mean for the D, we just need to add up sum of D divided by N. So when you add up all the D's, so we should get 22 divided by 10, so we get 2.2. So we have 10 data here for the D, so then the degree of freedom is 10 minus 1, which is 9. Okay, so we also need to count the variance. So 1 over n minus 1, and then we square the d's, so we get 188 minus sum of d 22 square over 10. Okay, then we count this, we get 15.51, and then we square root, then we get 3.9384. Okay, so we get the standard error or the standard deviation. Okay, now we can do the test statistics. So we use the formula. Okay, so 2.2 minus with the mu, which is 0, is from the H naught, from the null hypothesis, divide by SD 3.9384 over square root of n, square root of 10 for our case. Okay, then we count this, 1.767. So we get this t. So this is called test statistic, and after that you have to find out the t critical. Okay, so the t critical, of course you have to make use of the MF19 again. Okay, so let's say I put it down here. Okay, so MF19. So this is t distributions. This is normal. Okay, so this one, our degree of freedom is 9, so we refer to this row, and then the significant figures is 5%. So 5%, our H1 is more than, so that means 5%, 1.833, 1.833, yeah. Okay, so 5% is here, 0.95 is the other side, so 1.833. So we take this value, 1.833. Okay, so let's come back to the working here. So we get critical value as 1.833. So you just look at the graph just now. So we have 1.833 here. So this is the critical region. Okay, critical region is here. Okay, so you can see our value 1.767 is not in the critical region, it's somewhere here. That means we do not reject HO. Okay, so we just write down first. 1.767 is smaller than 1.833, and because of that, do not reject HO. Okay, so then we say that the mystical crystals do not boost IQs. Okay, so that's how we do it for this question. So this is two sets of sample, but they are pair. Okay, so now let's move on. Okay, so on this page, we have confidence interval. Okay, so let's see. Our confidence interval in general denoted by A to B. So that means this is the interval that contains the mean. Okay, so for example, okay, now, or you can write in this way, write in inequalities. Of course, they should have equal Okay, because you see they are using this kind of bracket. So when they're using this kind of bracket, that means it should have equal. Okay, so an A% confidence interval means that we will look up the critical value from the t distribution or normal distribution table where area under the graph is half plus a over 200. So to understand this, of course, we have to take example. So let's say our A% confidence interval is 95%. 95% confidence interval. So in this case, A is equal to 95. Okay. So what is half plus A over 200? So if you count it, then you will know something. You get 0.975. So 0.975, of course, this is the value that we should look at the MF19 just now. Okay, so it's something like this. 95% in the middle, 0.025 on the right, 0.025 on the left. So we are taking this value and we look for the corresponding value in the table. Okay, so this shaded region is 0.975. So that's why that formula helps us to count this. Okay. Now you want to find the mean, then you have to take a plus b over 2. Of course, the a is this a plus b divided by 2, and then you get the mean. Okay, you take the two lower boundary and the upper boundary from the confidence interval, add up and divide by 2. Not this a, they are using the same alphabets over here, but it's actually different. So if we draw from a normal of known variance, then the confidence interval is this formula. So this is to find the lower boundary, this is to find the upper boundary of the confidence interval. Okay, then if you draw from a normal of unknown variance, and then you have to count the unbiased estimator for the variance, and you get the S, then you put in the formula. The formula looks the same basically. Okay, now
So, what if?
yes.
Yeah, that's what I'm asking.
Oh, you mean this one, is it?
Yeah.
Oh, I see. Okay, so of course this one is under T distribution. You can see they are using T here. So then we have confidence, we have degree of freedom also. So V equal to n minus 1. So if we draw from any distribution where n is greater than 30, then the confidence interval is this one. So that means you have unknown variance, but n is greater than 30, and then you use Z distribution. Okay, so where the S is again the unbiased estimator. Okay, now next one, confidence interval for difference between populations. So you want to find the confidence interval for difference between population, the formula will be this one, x bar minus y bar minus c. So if you are wondering what is c, c is difference in means being c. So and most of the time c is 0 from what I found. Okay, so if the question mentioned any particular value for the difference, then you have to be careful, then you have to put the c here. Okay, so from two normal of known variance. So you know the variance, and then you put it here, you square, and then you put it in that way. So you can see this one is minus, this one be plus to get the confidence interval. So this can also be used for any population distribution of known variance given that n is greater than 30. So as long as n is greater than 30, we can use the Z as our confidence interval. Okay, so a little bit more, we look at this page. Different in means being c from any distribution of unknown variance given that n is greater than 30. Okay, so again we use Z, central limit theorem, we use Z. So same formula. It's just that this one we, instead of using sigma x, sigma y, we use the unbiased estimator as x, as y. Difference in means being C from two normal of the same unknown variance. Okay, so this is the pool. Okay, the pool estimate of common variance. You know, we learn this, and I say that they have the same variance between the two samples. Okay, so then you can use this formula. Okay, so the difference is they have the same variance, then they factorize the variance and square root, and that's why it's out here. Okay, so it's the similar concept basically. Okay, so we have finished out all the formula for confidence interval. Now let's take a quick look on some past paper. Okay, so let's say this one. A large number of runners are attending a summer training camp. A random sample of 6 runners is chosen. 6, not more than 30, you know. So this is t-test. So, and their time to run 1,500 meter at the beginning of the camp and at the end of the camp are recorded. Beginning and after. So seems like this is before and after, so related. So you have to use a pair sample t-test. Okay, so you have to find the D. The organizer of the training camp claims that the runner times will improve by more than 0.05 minutes. Will improve. Okay, so this one will help us to determine the H1. Okay, D is going to be more than 0.05. So we'll improve. So that means our D have to set up in this way. D has to be time at the end will improve. Okay, hold on. Let me think about it. If you improve, that means this is the running time. Okay, that means they will take a shorter time. If they improve, they will take a shorter time to finish. Okay, so take a shorter time to finish. So then we have to do it in the other way around. Time at the beginning minus time at the end. So okay, that's our D. Okay, now we put our D here. So our D is going to be minus the top minus the bottom, so end up with 0.1. The second one 0.07, 0.03, 0.03, 0.21, 0.19. Okay, so we get the D now. Okay, now we set up null hypothesis. The difference is 0.05. Alternative hypothesis, the mean difference is more than 0.05. Okay, now we find out the D bar, the mean. So we add up the D and divide by N. So we add up the numbers in the last row of the table. So you will get 0.63. Then we have 6 data. Okay, 0.105. Okay, then we count out the unbiased estimator for the population variance. So 1 over n minus 1 sum of d square. So you square the d and you add them up, so you get 0.0969 minus sum of d power 2 divided by 6. Okay, then you count this, you will end up with 0.00615. Okay, then we want to find ST instead. ST is 0.07842. Okay, now once you get ST, now we do the test statistic. Okay, so we use the mean, sample mean 0.105 minus with the population mean 0.05. This is from the H0 divided by the ST 0.07842 over square root of n. So we count this and then we will get 1.72. Okay, now we look for the critical value. Okay, so let's see the degree of freedom first. Degree of freedom is v equal to n minus 1. So 6 theta, 6 minus 1, we get 5. Okay, so we look for the theta booklet. MF19. Okay, so now not this, the T distribution. Okay, so our degree of freedom is 5. Our significant figures is 10%. Okay, so we look for 10% on the right. So we look for 0.90, 1.476. So we get this. Okay, so the T critical is 1.476. So imagine your situation is going to be like this. So 1.476 is here, 0.1, 0.9. Okay, now our test statistics, this one 1.72. 1.72 is in the critical region. So when it's in the critical region, we just write 1.72 is more than 1.476. So it is in the critical region and hence we reject H0. And then the conclusion is we follow the H1 conclusion, hence mu D is more than 0.05. Of course, it's good to write in words. You can just copy back the words. So copy back this particular part. Okay. The runner time will improve by more than 0.05 minutes. So you can do something like that. Okay. So this question finished. Okay. So we finished this chapter already.